Hello everyone, how's it going? Today we will be learning about extrinsics, transactions, transaction extensions in Polkadot SDK by Guillaume. Guillaume is an engineer in Parity. He's also a fellowship member. Yeah, today is going to be very informative. If anyone is looking to extend like what they can do with transactions in general, this is a great call. So if you have any like questions right now, you can put them all in the chat and we would pick them up 40 minutes into the call. All right, thanks. Okay, please take it away. Thanks.
Thank you. So yes, today I want to talk about the transaction in Polkadot SDK. So since I think in December of last year, there is a signed extensions that is replaced by transaction extensions. So what I want in this presentation is to give the global logic behind transaction extensions so people can really use it fully. So I guess let's go into the presentation. Oh, so I'm Guillaume Thiolliere, but yeah, the presentation about me was already made. Okay, let's go. So first I will just talk about the transactions as a whole in the blockchain, through the nodes, to the runtimes, to the blocks. And then we will go more deeply into the programmability of the transaction inside the runtime. So we just take a transaction from a user. The user sent to the node. The node receives a new transaction. And the node basically has two main components, which is a transaction pool, and it follows the blockchain state. It's a simplified view because actually it follows like the blockchain state at multiple blocks to be able to adapt in case there is a fork or stuff like this. But we will just take a simple view. There is a transaction pool and there is a blockchain state. Inside the blockchain state, there is an important key, which is a runtime. So inside the state, the runtime implemented is stored. It's just a binary of WASM code. So we have these three components: new transaction, transaction pool, blockchain state. What the node do? It spawn a VM instance with a runtime code, the new transaction, and it executes a function inside this code, which is validate transaction. This gives to the node valid transaction information, or if it's invalid, it just discards the transaction. This valid transaction information is useful for the transaction pool. You get the longevity, some tags, a propagate flag. What are the tags? Tags is simply a way to order transaction pool, to order extrinsic inside transaction pool. So there's a required tag, provided tag, and then we can make it first you put transaction that provide something, and the transaction that requires the thing that was provided. It's a way to order transaction inside the transaction pool. But this is not the main point of the talk, so don't need to go so precise on this. So then it includes the transaction inside the transaction pool, propagate the transaction in case the transaction is signified as to propagate. And that's it. So now the node is waiting to produce a block, or waiting for blocks to come to him. The interesting event is when it wants to produce a block. When it wants to produce a block again, it spawns a VM instance, WASM VM instance, puts the runtime code, and builds a block. When you build the block, you put transactions from the transaction pool one by one, and it executes them. There is actually multiple hooks to build the block. There is like first you run the initialize, then your execution of each extrinsic, and then on finalize, when you have a full block. When you receive a block, you have another hook, which is just execute blocks, that doesn't matter so much. What is important is that each extrinsic, and in our case, each transaction will get executed in the block and will produce then the state for the next block. When I say extrinsic or transaction, here I talk about transaction because we talk about something that comes from the user, but in Polkadot SDK, we talk about extrinsic because not all element of the block is a transaction from a user and goes from the transaction pool. There is some other elements such as inherence, which is not a transaction and never go to the transaction pool. So a transaction is an extrinsic. An extrinsic is either transaction or inherent, or maybe something else in the future if we have a usage. Okay, that's what it for external transaction. I think it's simple. Maybe I don't need to summarize so much. User send, the node receive, the node validate, put in the transaction pool, and then when it is building a block, it will execute the transaction. So inside the runtime, there is basically two hooks, validate and execute. I said external transaction because there is also another kind of transaction. It is a local transaction because it comes from the node itself, not from a user. And the source is kind of trusted. For now, there is only way to get a local transaction is through the off-chain worker. So what is the off-chain worker? This is also a function implemented into the WASM code. So every time you receive a block as a node, you will execute this off-chain worker. Every time you receive a block, you spawn a VM instance with the runtime code, and you execute this function off-chain worker. This will give the node some transaction. It will submit some transaction to the node. So you have now like a new local transaction, but the code that generated the transaction is stored on the blockchain itself. It is trusted because it's part of the protocol. So you can see that you can't be DDoS by the blockchain you are validating. Like, it doesn't make sense. The protocol will not DDoS yourself. So this is a trusted source. And this is why we make a distinction between external and local transaction. And then the CI code is the same as a new transaction, but it is local. So we validate it, and we get the information, and we put into the transaction pool. Put in the transaction pool, propagate if it's set. The flag is set as propagate, and then when we build the block, exactly the same. Because it's just a normal transaction, it gets put into a block, and as part of the block, it will get executed into the block. So basically, the same lifecycle, just the way it is created is not from the user. It is created from the off-chain worker, which is a code that is run by the node after receiving the block or producing the block, after a new block is added to the blockchain. And here, briefly, I can talk about inherent, but it's not the main point of the talk, so you don't need to, it's not, I will explain just quickly. So there's inherent data, which is like a view of the world from the node. It can contain the time, like a time is something that the node has it's a conception of time, but there is nothing like a true time. So this is kind of the inherent stuff that are part of the inherent data. And then it will also execute something that is inside the WASM runtime code, which is provide inherent. And this gives some extrinsic, which are inherent. And this inherent, they will not go into the transaction pool. They will directly get included into the blocks that the nodes want to produce. So before producing a block, the node gets the inherent from the runtime code by calling provide inherents, get some inherents, and they will include them in the block. So yeah, so that's kind of all for the first part here. Basically, we have what is an extrinsic? It's a transaction or inherent inside Polkadot SDK for now. And transactions are either external or local. They always go into the transaction pool and get into the block when the block is produced. Inherent, they are not going to the transaction pool and they get into the block that they are generated for. When building a block, we execute inherents, we execute transactions that we have put into the block. And when importing a block, we execute also all extrinsics, so all inherents and transactions. So this is the first part. Basically, times the runtime is used for transactions, for the validation, and for the execution. So now we want to implement in Polkadot SDK how we can make it programmable and how we can easily extend this implementation of transaction inside the runtime. So this is what we have. We have a type extrinsic that we will have to define. We will have a primitive types, which is a valid transaction information, which is for the transaction pool and such components. So as we said, there are the priority, the tags, the longevity. I list this one. The longevity is basically after the longevity has passed, you have to recheck it, I think. Or maybe they even discard it directly. I think they recheck again. On the propagate flag, whether you have, when you receive this transaction, you want to propagate to other peers. And the runtime has two hooks implemented, which is validate and execute. And the validate returns the transaction information, the valid transaction information. Interesting as a result, because if the transaction is invalid, if the validation is failing, transaction is invalid, should be discarded. If the execution is failing, the transaction is also invalid, and the block is invalid and should be discarded. So we will start by the most simple transaction. Simple transaction comes from a user, is assigned, has a signature, and in frame, there is a runtime call. Parity define calls, this is according to the runtime call. So usually we do like this. We get the runtime call, and we define the extrinsic with just a signature and a signer. Then when we want to implement the validation, we just need to check the signature that the signer actually wanted to, intended to dispatch this call to this blockchain. Like the call can be send, can be just any transaction, like send 10 dots to Bob, signed it, send the transaction. We validate it by checking the signature. When we execute, we check the signature again. Because the transaction pool stuff is kind of off-chain. So when we execute, we want to do all the checks. So we check the signature again. Signature is good, so we say that the origin is signed, and we dispatch the code with such a signed origin. Okay, this was very simple, and you probably know that this is way not enough. Like there is tons of checks to do more. We want to prevent replayability. When a user sends a transaction, he doesn't want another user to send the transaction again. Like you want to send 10 dots only one time, not if the other person just send you the transaction you have signed again. You want this to be invalid. So there is a note, but we will go into this. So replayability is one thing. The spam protection, or like the usage of the chain. So usually it's the payment of gas or payment of weight in the Polkadot SDK. We want to be sure that the transaction fits into the block. So there's a block limits. So all those checks, we want to have a trait and to implement all those checks like as an implementation of a trait. So this trait is a transaction extensions. For now, it will look very similar to the signed extensions. And later we will see how we extend it. So transaction extensions, basically two functions, prepare and validate. Validate and prepare. Validate will hook into the validation process, and prepare will hook into the execution process. So prepare will be executed just before the dispatch. In extrinsic, we add this new field, the extension. In validate, we hook, so we want the extension to be part of the signed payload, because this is extensions will contain information that are also intended by the user. So users have to sign it. So we construct the concept of signed payload, and it will have the call and the extensions. Basically, all what the user intend to execute on chain. We check the signature. Then we execute our hook, self extension validate. And in execute, what we add is just this line. So we call the prepare of extension before the dispatch. So let's use it now. We can use it for implementing check nonce. This is exactly as what is written. I mean, not exactly, but conceptually, this is what is written in frame system extensions, check nonce. So nonce is a way to protect replayability. The way we do this is just the user just numbers the transaction it sends. And on-chain, we track this number. So user sends a transaction with the nonce number 0 at first. So we put inside the transactions this information. Check nonce contains this nonce, and it will be part of a signed payload. So part of the intent from the user. And when we implement validate for this check nonce, we check the on-chain nonce stored for the user, and we ensure that it match, or we ensure that it is plus. I think this is the case. We ensure that it matches. If it matches, it is valid. We can dispatch this transaction. And in prepare, we want to execute the logic for this transaction extension. So we increment the storage. We increment the nonce stored in the storage. So when a user dispatch with the intent to dispatch the transaction number 10. 10 matches the nonce that is on chain. The nonce is incremented to 11, and we have a replayability protection. Then, because we have defined extrinsic generically, we can just, for our blockchain, make it a concrete as an extrinsic with one check, which is a check nonce. Another check, which is very similar, is replayability in other context. So we have protected the transaction to be replayed in the same blockchain, but maybe if you send a transaction to one parachain and another parachain has the same format overall for its blockchain, you don't want the transaction to be replayed in the other parachain. So for this, you will sign for a specific genesis hash, which will show the unicity of. Through this genesis, through the signature of this genesis hash, the sender can give the intent to sign for a specific blockchain. So how do we validate for this? We have the hash, the genesis hash on-chain. So we just compare the given genesis hash to the on-chain genesis hash, and if it doesn't match, it is invalid. If it matches, it is good. And then for your blockchain, we can implement an extrinsic with two checks, check nonce, check genesis. But here we haven't specified how to accumulate checks as a tuple of multiple checks. So we can do this quickly. Let's focus on this first. There is a trace. It's very handy from a crate made by Basti, so implement for tuples. So we can reuse this. And we basically implement transaction extension for a tuple of transaction extension up to 12 elements. For validate, we execute the validate for each element of the tuple, and we combine the information resulting from the validation of each element. And for prepare, we just execute the preparation of each element of the tuple. How do we combine elements? The priority is added. Tags are concatenated. Longevity, we take the minimum, and propagate, we take the end of each propagation. And then we can define our blockchain as just a multiplicity with a multiplicity of checks. And the way we implement this is transparent for how you organize your tuples. So you can do tuple of tuples like this, A, and then tuple of BCD. If you have more than 12 elements, this can be handy. It can be A, B, C, D. The way we define the combination rule and the way we define validate and prepare, it will be equivalent. Okay, so we have basic checks, multiple checks inside our transaction, but we saw Genesis, check Genesis, but there is one optimization, and we should do so. We saw in check Genesis that the hash was stored on chain, and when the user sends a transaction to a blockchain, he intends to send it to the blockchain it sends it to. So let's say this. We don't need to store the Genesis hash in the transaction itself. We just want the user to sign for it. So here we have saved this extension, but for our check Genesis, we just want to do the signature of a call on the Genesis hash. We don't need to store the Genesis hash in the transaction itself. Remember that this defines the transaction extension, so it's part of the transaction. Why is it important? Because we want to keep transactions small. If the transaction is small, blocks is small, everything is smaller, it's better it's more efficient. So to solve this issue, we will bring a new concept, implicit and explicit. In the previous version, it was additionally signed was implicit, and explicit was just the normally signed. So we renamed it to the new concept, implicit and explicit. So implicit is something that is not part of the transaction, but it is part of the signed payload. How we defined it? Transaction extension, take a new type, implicit, generic type, and take a new function, implicit, which returns the implicit for the transaction. I mean, it creates the implicit to put into the signed payload, given the current state of the blockchain. And we use this new component of the trait when we define the signed payload. So the signed payload is now the aggregation of the call and the implicit and the explicit. We check the signature same as before, and everything has remained the same. A small addition is that validate also receives the implicit as an input because it's good to have. It avoids to query the storage multiple times. But it's equivalent to calling implicit again. It's just an optimization. So let's rewrite the check Genesis using the implicit. Check Genesis itself is nothing anymore. It's just a check, but it doesn't add any byte to the transaction itself. We define implicit as a hash, and the function implicit just checks the Genesis hash from the state on chain, returns it. And in validate, we have nothing to do anymore because what was important for us is that the signed Genesis is matching the on-chain genesis. But here we implicit is on-chain genesis, and it's part of the signed payload, the generated signed payload, so we are all good. We checked for the intent of the user without having the explicit intent inside the transaction. So yeah, implicit, explicit is good to reduce the size of the transactions when you just want to sign for stuff, but you don't need to have them in the transaction. So okay, replay protection done. And the weight limit, it's to explain a bit. There's also spam protection, but spam protection is very similar to what we saw. It's just on validation. We just check the balance and similar stuff. So weight is more interesting to see, and because in the later when we will do the general transaction, weight will be greatly changed. So it's important to dive into this. So what are weights? In Polkadot SDK, basically weight has two dimensions. Kind of a gas, kind of like a cost of an operation. The two dimensions is the time to execute. So we call it the rave time. It's the name of the field, I think. Rave time is the time to execute a piece of program on a reference hardware. So the weight of the program, the rave time weight of the program will be something on a reference hardware. And the other dimension is the proof size, because the parachains collectors bundle a proof alongside the block, and the cores execute the state transition function of this block using this proof. Basically, the proof is the storage access. So when you do storage access, you bundle the storage access into the proof, and when you verify, you can query the storage from the proof. So every time you do some storage access, it increases the proof size, and this is the main component of the proof. So weight has two dimensions: computation time and the proof size, mainly storage access. You can define some type. Two types, basically dispatch info and post-dispatch info. Basically what we want is to define the ahead of dispatch, we want to know the worst case weight of the call. And after the dispatch, we want to know, it's good to know the actual weight of the call. Before dispatch, we may not be able to judge exactly how much weight it will cost. So after dispatch, we can have a more accurate information. So dispatch info, basically pre-dispatch info, and post-dispatch info. After executing the call, we can have a more accurate weight for the call. And we define a constant, which is base weight. Base weight, it contains the weight for the signature verification and for the transaction extensions. And this is changed also. But for now, we'll define it as a constant. Usually we benchmark for it, and we benchmark for the blockchain. Okay, so now we'll extend the traits, transaction extension, to have access to those new information. So basically, we add the information everywhere. In validate, we have access to the pre-dispatch information. In prepare, we have access to the pre-dispatch information. And we also add a new hook, which is post-dispatch. Post-dispatch have access to the pre-dispatch information and the post-dispatch information. Okay, in reality, we have more than this. We have also the length of the transaction. And we have also the result of the transaction. The result of the transaction is not making the transaction invalid. Like when you send 10 dots to Bob, and you only have 5 dots. Maybe 5 dots is enough to pay for the fees, transaction fees. So you can pay for the transaction. The transaction itself is failing. You don't have the 10 dots. So in this case, the transaction is resulting in an error, but it is valid. So we have to be careful about dispatch result and transaction validity. I put it as informational. Actually, we will not use it, but it is there. So now we will implement the check weight. It is also in frame system extensions. Check weight, we will have access to the weight. So I put into too much details, but basically in validate, we calculate the weight and we check that the current block weight that we are building for doesn't exceed. Then in prepare, we accrue the current block weight. In post dispatch, we reduced with a more accurate version. I think it doesn't require to go so much into detail. What is important to know is that we have access to the weight before dispatch. During prepare, we make the weight effective. Like we take into account for the current block weight that we are building. And in post dispatch, we make a more accurate version. Small information. Also, we have some type to allow to easily send information from the different stage. This is quite minor, but like you can send information from validate to prepare, and from prepare to post dispatch using those two generics. And another small information. We saw previously there was two transaction source, from a user and from a local. It's good to have them also in transaction extensions because the local is more of a trusted source and you are not vulnerable to denial of service. So we can do more expensive checks inside the validation if it's a local transaction. So we also have the transaction source inside the validate function. And the third variant is in-block. Like what is an in-block transaction? Basically, when we are building a block, or when we receive a built block, the transaction is used come from a block. It doesn't come from a local source anymore, or external source anymore. It's just a block. Okay, so maybe I went fast a bit, but all I explained now is not exactly how signed extension was working, but the feature is exactly the same. So now we will see what is new. And this is it was a long introduction, I guess, but this is a interesting part. But now that we built the preliminary, actually what's coming next is quite not so difficult. So first, we made it the transaction extensions declare their precise weight, pre-dispatch and post-dispatch. Previously, it was part of the base weight we saw. Base weight was a signature verification weight plus the transaction extensions weight. But in quite some cases, we want to do expensive operations inside the transaction extension. So we can't have this base weight anymore. So what we added is actually the transaction extension weight. Transaction declare its pre-dispatch weight. And inside the post-dispatch, we also register the transaction extension weight. But you can see now that, okay, we can't have a post-dispatch of like when we execute a post-dispatch of the first element of the pipeline, of the first transaction extension, we don't have yet the final post-dispatch information because the second element didn't refine its weight yet. So how it is done, that in post-dispatch, we have a multiple reference to post-dispatch information. This multiple reference is basically every step of the pipeline will refine its weight. And at the end of the pipeline, you will have the final refined weight of the transaction. So now it's not an accumulation of checks, it's more like a pipeline. The concept of pipeline is very useful also for later. Okay, what is implemented is actually, there is a function post dispatch, but because of this multiple reference, it's a bit annoying to use. So what we created is a more user-friendly method, which is post dispatch details. Takes a non-mutable reference and returns the unspent weight. And then post dispatch is automatically implemented to call post dispatch detail, get the unspent, and reduce the post info using the unspent received. So what you implement is actually this function, post dispatch details. And the return element is the unspent weight. So basically you can return 0 if you are if you don't want to refine further, because you say you have used all the weight. So 0 is unspent, and this is safe. Weight was the first part of what we added, and there is only one second part, is the generalization of transaction extensions. Basically, what we saw in our extrinsic was that it came from an account ID with a signature and it dispatched a signed origin. But this is too limiting. We want the transaction to be able to determine the origin of the transaction. It can be signed, or it can be a person, or it can be something. And we also want the transaction extension to determine the way it validates this origin. So for now, we have hard-coded that the extrinsic has a signature validation to a signed origin. But we want to push this into the transaction extension trait, so the transaction extension can define what is the validation logic for the origin it wants to determine. And also the transaction extension will be able to determine the origin to dispatch the call. We use it in proof of personhood because we want to dispatch as a person and no longer just as a signed account. So the goal will be for now to implement a new transaction extension, which is verify signature. And the verify signature is the check of a signature and the determination of a signed origin for a transaction. So this is the concept of the transmutation of origin. So we have our pipeline of transaction extension. We'll start the pipeline with the origin none. And each element of the pipeline will be able to determine the origin for the transaction. So it will receive the origin prior to itself. So if it's the first element, it will receive none as the origin. And it can return the origin for the following of the pipeline. So a verified signature will return a signed origin if it is successful. And at the end of the pipeline, if the origin is still none, if no transaction extension determines an origin different from none, it means that the transaction is not authenticated to any origin. So it is invalid. So we start the pipeline with none. A transaction extension receive each transaction extension or each pipeline element receives the origin from the previous stage and determines the origin for the next stage. So how do we use it in verify signature? Yeah, basically first we have to make this transmutation of origin available in the method signature, the method types. So validate takes an origin and returns an origin if it is valid. And this is our implementation of verify signature. It is also inside Polkadot SDK. We want to make it optional because maybe user want to skip it and use a personal verify person or verify entity or another verification process. So we make it two variants, signed or disabled. If it is signed, we take the same information as before, a signer and the signature. And when we implement validation, if it is disabled, we just give no specific valid transaction information, and we don't refine, or we don't determine the origin further. We just keep the same origin as what was previously determined. And if it is signed, we will first ensure that the received origin was known. Maybe this check is not really necessary, but maybe it's safer. Like if the origin was a person, we don't want to make it signed. Yeah.
Use this, yeah. So our Discord is quite good as well. There's actually a call happening even like the educational call. So every Sunday we usually have those educational sessions. It's a good place to be, I guess, if you want to learn more. And there are mentors there as well you can interact with.
So you want to take?
Yeah. I'll send you the invite. I'll send the invite in the chat.
I have difficulties to understand. Okay. Right. But if you wonder about when you can ask questions, it's actually almost finished. There is after transmit, there is another concept to implement this, and then final few slides, but nothing further. So we are almost there.
Could you also maybe show where we can find this transaction extension code within the Polkadot SDK for like reference purposes?
I see. So this is all in the Substrate primitive runtime. So inside the repo is called Substrate primitive runtime and the source. And inside this, you have all the primitive types. So you have this extrinsic, which is actually named unchecked extrinsic and checked extrinsic. And for the transaction extensions is also inside a module transaction extensions or traits, same transaction extensions. But all inside the runtime primitives. The crate name is sp-runtime. And the verify signature is inside the frame, so it will be a substrate frame verify signature.
So yeah, I would paste the link to the code in the chat so we can use that. Use the recording that is going to be out in a week. Use the questions from the chat as well to sort of, find your footing around the SDK.
Okay, so we had the transmutation of origin inside verify signature. And here we check that the prior origin determined was known, just check that we don't mess up some double check and so erasing some checks. And if it's correct, we return the signed origin, but we don't have payload anymore. So this is our issue. And this is the final point of general transaction. How can we estimate a payload for our pipeline when it is kind of dynamic? We are inside the pipeline already. And this is a concept of inherited implication. So maybe first I will just say how it is implemented, and then the usefulness will come out of it. So inherited implication is just the explicit and the implicit data for the rest of the pipeline. So if you're in the validation of B, the inherited implication will be the explicit of implicit of C, of D, and also at the end of the pipeline, there is always a call that is intended. So also the call. And if you are in C, you have the explicit, oh, I forgot. So the explicit and implicit of, I can't write. Anyway, okay, explicit and explicit of D on the call. And if you are in D, the inherited implication is just the call. So what we intend by this is that when when one element wants to determine an origin, it will determine an origin for the intent of what is further in the pipeline. What is before is already gone. Can't access it. So this is why there is a direction inside those checks. And in verify signature, we can use it like quite straightforwardly. So we have access to the inherited implication here. And now we do our check just by taking the inherited implication. We call it uncode, but this is just a detail. We have our signed payload, and we check the signature on this payload. So we have abstracted our signature verification inside the transaction extension. We have this new trait implication, but just bonds uncode. Because what we do is just uncode it and check some signature usually. At least I never had any other use case. And now, so this is the usage inside the definition of one transaction extension, but we have also to define how we use it inside the extrinsic types. So the extrinsic types no longer check a signature, no longer take a signer, just take a call and the extension. And then validate just calls the validation of extensions themselves. There is no longer hard-coded steps. Execute. We execute the validation again. We get the origin resulting. Oh, okay, I forgot. This one will be also added here because we want to be the transaction is invalid if the pipeline has ended with none. Okay, but at least the execution implementation is correct. Sorry for this miss. So in the execution, we have the validation. It gives us determined origin. If the determined origin is still none, means that it is invalid. Then we have the preparation, the dispatch, and the post-dispatch. Then when we define our extrinsic, we can just define our verification extension first, and then use the usual repairability, spam, etc. transaction. If you want a more complex pipeline, you can have like verify signature, verify person, and then other element of the pipeline. Yeah. So, but you can see there's one difficulty. Like we saw check nonce. Check the nonce for an account ID. So actually check nonce is only implemented for signed origin. So if you determine the person origin for your call, there is no replayability protection anymore. So in our case, for proof of personhood, we defined another extension for the payment, another extension for the replay protection of a person, etc. So yeah, this is what I said by difficulty. Some previously implemented checks are only implemented for specific origins, so we should be careful. For example, replayability, also spam protection. So in proof of personhood, we made some additional extensions. Okay, this is the last slide. Basically, Extrinsic is not what I described before, because we want to be backward compatible and we want to handle inherence. So this variant is a bit useless in principle, but useful to be backward compatible. And this is basically what was this variant that was existed before. The signed origin. And the general is a new one. And we no longer have a signature on the account ID, we just have a code on the transaction extension. And the bear is used for inherence, also for unsigned transactions, but I didn't precise in this talk what unsigned transactions are about. But unsigned transactions basically can be re-implemented as general now, so we want to deprecate them. So we have this extrinsic, and now because we want to also hook into the execution and the validation of bear, we also have 3 new methods specific for bear. And this is what is in Polkadot SDK. So yes, SP runtime. You have extrinsic. The type is a bit more complex because it has some generics or some stuff, but if you look at inside the type, you will really see like a 3 possible instantiation of this type. 3 variants of this type. And those functions are exactly correct. This is the exact name of what is in transaction extensions. So what we have is this. Transaction extensions, some types to give from stages to stages, implicit, which is part of implication now, but signed payload, if you want to do it conceptually. The wait, validate, which take an origin and result a determined origin, or the same. Prepare, post-dispatch, which returns the unspent wait. And the post-dispatch, which is automatically implemented, with calling it to post-dispatch details and doing the refinement of the weights automatically. And the free transaction for bear extrinsic. Actually, that is all. I have additional slides, so when there's questions, also maybe I can show them. But I think that's all for what I wanted to say more importantly. So thank you for attention. Also, thank you for Polkadot Africa for the invitation. It was great to be able to talk about this.
Thank you for that, Gui. I think we've all been impacted meaningfully by this talk today. Yeah, if anyone has any questions for Gui, you could leave it in the chat, or you could unmute yourself and speak out so that we can, address your questions.
Yeah, I think I have a few questions. Hi, everyone. Thank you, Jui. Thank you for gracing our Discord server and coming into our coming to be a guest in our runtime session. I mean, if for people who didn't join on time, what we learned today was transaction extension, and also the different ways the transaction extension is useful for your runtime development. So I have a question now. What is the difference between, why should I use transaction extension? Why not just a normal transaction type?
Yeah, so the only, the most important reason is when you want to have a special validation logic. So transaction extensions allows you to hook into whether a transaction is valid or invalid. When you implement the call, the transaction is already valid. The transaction has already been paid for, has already protected the sender for the replayability, and the transaction is valid. That means that except if you panic in the runtime, but you shouldn't do this except in very special cases. The transaction will be part of the block. It will execute to the end. You may result in error, but the transaction is part of the block. And some people has pay for, and it is good to go. So really, the most important reason is when you want to give specific validation. That's why it's not really related to the code itself, because you can see like a transaction can submit very much different calls, but it's more related to the sender, to the origin itself.
Okay. Thank you. I think there was a chat in the chats. I don't know. Did you check Jesse, did you check the chats if there was
Yeah, I asked a few questions in the chat, which I felt were relatable to anyone building runtimes or contributing to the SDK, but someone already answered all of them. So shout out to that person. Hope we can have you more frequently.
Okay.
Yeah.
All right then. All right. Useful. This was a very, very insightful space. Thank you, Julie. Thank you. From Polkadot Africa, we are grateful to have you in our presence, and we look forward to having you more often during our runtime call. Jesse, do you have anything to say?
Yeah, it was a great session. I think we all learned a few things about transactions in general and how to extend it. So
Okay,
thanks, Guillaume.
thank you. It was great to speak.
Hey, everyone, have a great weekend. Have a great weekend. Make sure you rest. Next week is a big week for everyone. Wag me.
Log me. Have a good one, guys.
Yeah, definitely want to see it. Okay, but we can just see. Okay, should I say goodbye then? Goodbye all. Thank you.